Hello everyone, I'm George and today I'm very glad to see you through the internet. As we know, due to the serious epidemic situation, I cannot meet you in person, but I'm still very pleasure to see you all and feel the enthusiasm in AI from all of you. Today I will talk about the AutoML and some related AI open source projects. Before that, let me introduce myself. My name is George Cheng, AI Infra Engineer from Such Technology Center in Microsoft. And below is my GitHub and Twitter accounts. Looking forward to your stars and follows. Okay, let's begin. This is the agenda of today's talk. Firstly, we will look back the challenges in current machine learning modeling and how AutoML solve it. And then we introduce some concept and the process of AutoML. Next, let's dig into the AutoML toolkit called NNI. Finally, let's use the NNI to tune a machine learning model. Next pages will include lots of touch details, so I will turn off my camera and enjoy my slides. Currently, we have lots of challenges in machine learning, from datasets to modeling. When the dataset is prepared, we often need to choose a suitable algo in a big number of machine learning algos. Also, new algos are keeping coming out. For example, this graph says how to choose the most suitable algo when using scikit-learn. As we see, it's based on the data size, quality, labeled, also the learning aim. And we should use different algos. After the basic filtering, we usually still have some algos to choose, and what we can do is just try them one by one, and finally we find our Mr. Right. After choosing algo, we still need to know the hyperparameters of the algo. As we know, different algos have different hyperparameters. Each of them will affect the training result in different ways. Though we have the knowledge of affection of each hyperparameter, to find out the relationship with the model and the dataset, still needs some experiments. Besides that, machine learning requires lots of computing resources. If we do not have a good plan in training, the training progress and the manual analyzing progress will be the bottleneck of each other. Just like when computer finish some training of the model, data scientists need some time to plan the next cycle based on the result of the current round. During the planned time, the computing resource is idle, so the efficiency seems to be decreased almost a half. So how do we meet these challenges in machine learning modeling? Firstly, we can summarize some experiments and find out some generalizable patterns. For example, for some specific network, the learning rate seems almost stable, like 0.01 is a good one. We can stabilize this value before the actual tuning. On the other hand, there are still some uncertainties, just like batch size. It's related to the size and the characteristics of the datasets, but we can know the scope of the uncertainty. We could try many times to optimize it during modeling. Besides, we need to improve the efficiency to schedule the computing better to reduce the bottleneck between manual works and computer work, just like I said previously. So, to meet the modeling challenges of machine learning, we cannot ignore the value of AutoML. AutoML could be understood to the algorithms built on machine learning to learn the hyperparameters. In other words, We can simply call it machine learning of machine learning, or using machine learning ways to learn hyperparameters. After we got AutoML, we could simply think that the whole training progress is that we filled AutoML algo with datasets, and we got a model. The model could be directly used to infer. So inside AutoML, there are lots of things happen. What it's doing is actually we treat hyperparameters as normal parameters to train in classical machine learning. So we need to understand what is parameter and what is hyperparameter, right? Firstly, parameters are possibly tens to billions of values. Most of them are tensors, like metrics or vectors. These values will be tuned through datasets, and we got the potential loss in datasets. We call it knowledge. Okay, so hyperparameters are parameters we need to manually set and difficult to be tuned automatically, like algorithms, cycles, learning rates, numbers of neurons, neural architectures, etc. Let's say an example. From the training start, we need some hyperparameters to determine something like cycles or using which algo. And during the training, it's validated by the model trained. During the validation, the parameters are updated back to the training progress. Usually, it's based on the accuracy. And when the training is about to be finished, the model will be tested. We mainly test its generalization. If we get a good result in validation test, we will release the model for inference. And the model is made up of parameters and hyperparameters. So we can see that the hyperparameters are very important in the AutoML progress, but it have to be set at the beginning of the training, not like parameters. There's another concept in AutoML called search space. Search space is that which hyperparameters we chose and the value range of the chose hyperparameters. If we decide to make a big search space, we can hardly miss the best hyperparameter tuples, but we need more computing resources to do it, of course. If the search space is smaller, it needs fewer computing resources, but it's possible to miss the best tuple directly when we decide the search space. Hyperparameters in such space are basically some basic data type, like enum, integer, or some floating numbers. The enum and the integers are usually limited numbers and easy to decide. But floating numbers is continuous and have a big value change. Generally, we decide them piecewisely to narrow the search space. In each piece, we decide the values by its distribution. The distribution is something like even distribution, normal distribution, or exponential distribution. For example, learning rate. We often make the values exponentially. Like we have a learning rate range .1 to .001. We will make 10 values between .1 to .01 and another 10 values between .01 to .001. Which makes a better AutoML search space. There are mainly two algos in AutoML, optimization algos and evaluation algos. Optimization algos is to generate some hyperparameters to train. Some optimization algos are able to decide the next tuple of hyperparameter based on the final results. This will improve the efficiency of the hyperparameter generation or try to generate the hyperparameters that will cause better results, or the range did not touch. Other kinds of algos are called evaluation algos. The training will send intermediate results to evaluation algos. It will decide whether it should be early stopped. In this graph, the intermediate and the final results are actually the optimizing targets of the model, like the data or the data of accuracy or loss. Okay, next let's see an AI open source project from Microsoft, NNI. Full name is Neural Network Intelligence. The purpose of the project is to make a lightweight, easy to use, and extensible AutoML toolkit. It's open source on GitHub. You could visit the project by the link address of GitHub. NI is a lightweight but powerful toolkit which could help users to automate the feature engineering, neural arc searching, and hyperparameters optimizations, model compression, and many other cases. In the NI scenario, we can experiment different AutoML algos and also speed up learning in many kinds of distribution environments. Also, we can quickly experiment or implement new AutoML algos. In addition, users can use NI to support AutoML in their own machine learning platforms. Let's see some highlights of NI. NI is independent of frameworks and platforms. It supports the common frameworks and libraries and lots of examples. In NI, we could simply use PyTorch, Keras, TensorFlow, CNTK, scikit-learn, LightGBM, and many other libraries. With the following libraries on the slides, user could get started with the examples we provided already. NI also support many types of training environment and platforms. Firstly, NI supports the local machine training. And if the user is able to access the remote machine via SSH, those machines could also be able to be made as NI serving nodes to run the experiments. And the NI still supports the training platforms like OpenPy, Kubeflow, and others. NI integrates lots of AutoML optimization algos, including some hyperparameter optimization algos like TPS, SMAC, Naive Evolution, and Grid Search. It also has some brand new algos like the Hyperband or BOHB. Almost 10 several hyperparameter optimization algos. Besides, it has up to 10 algos of neural arc searching, like ENS, stars, and network morphism. NI also supports multiple AutoML scenarios in addition to hyperparameter optimization and neural arc search, like model compression, feature selection, and other optimization systems. NI is very simple to get installed through pip in Python, just like this command, python 3-m pip install NI, and you got it. Besides, if you are interested in the code or want to do some contribution, NI also support to be installed from the source code. There are 3 steps when using NI. The first one is to define the search space and then add to code with the hyperparameters in search space and give back the intermediate result and the final results. Lastly, we have to do some configuration. Let's see from the step 1, the search space definition. In this code, we can see there are 4 hyperparameters selected in to be the search space, including dropout rate, conf size, which is the convolution sum. Third one is hidden size, or just fully connected layer size. And the last one is learning rate. After we got these four hyperparameters, we add the nni.get parameters to code to get actual values of to get the actual value of the hyperparameter to the actual training code. And in the code, we put the parameter to their position in each batch size or other suitable moments. We could report back the intermediate results. The intermediate result could help to decide whether the trial should continue, or the result is too bad, no need to continue. Finally, to report the final results to the hyperparameter to the hyperparameters optimization algos, which will decide the next tuples of hyperparameter. It will be generated to make the search more efficiently. Finally, there are some configurations. The configuration could decide these trials could be run in how many scenarios in parallel, such as if we run in the scenario of local machine with 8 GPUs and each trial use 1 GPU. We could set the concurrency to 8 to maximize the learning performance. Also, there are max execution duration, or max trial number to get the final results. Below that, we could choose a tuner from many NI tuners and tell NI how to run the code, also how many GPUs it needs. After the configuration of search space and NI itself, and also added the code of report results and get hyperparameters, we could start our NI experiments. Starting the NI experiment is very simple, just one command, nnictl create, and the path of the config file. After starting, we could get these outputs. The yellow highlight is the URL of the web UI. Open this link, we'll access the web interface of NI to monitor and analyze the result of the experiment. This is the index page after NI started. We could get the key information in this page, like when did it start, when did it end, and which platform did it run on, where's the log, etc. In this experiment, we could see that the experiment is done. The status is done. Cost almost 40 hours with 300 trials. The best result got 92 scores, which stands for the accuracy is 92%. There's also concurrency count. We could adjust the concurrency count during running. At the middle, there is the search space. In such space, we could see every value in the search. You can see there is a scroll bar, so we are able to see the whole search space. At the right, there are configurations. We could see that we are using SMAC tuner running in local machine. Below, we could see the best results in time. Because there are accuracies, so the results are ordered in accuracy. Max accuracy goes first. Also, their distributions. Let's see the result in detail. We could see its detailed data by a click. There this is the number 132 trial, which is the best. Its hyperparameters are listed here, including batch size, conf size, and the dropout and others. Combining all of these parameters will build the best results. We could see that it ran about 1 hour and 4 minutes, and the score is 92.36. This is a very simple network for our demonstration. Besides the best results, we want to see some others like the searching progress. We could go to see default metrics in detail page. In this chart, we can see in SMAC search, the best result is at number 132. Before that, at the beginning, we ran many trials and found some low scores and became higher to the number 132. After that, it started more trials and found more scores, but no more higher. So algos like SMAC is good to find a good result in this kind of machine learning. After we run some trials, we could analyze the relative fitness between the hyperparameters. Now we selected the best 20% results to see the relationship between hyperparameters, and we can find something. Just like for learning rate, basically the best learning rate is between 0.001 and 0.01, and also nearer 0.001. For momentum is near 0.9. For drop rate is about 0.5. These are some other related hyperparameter and also some not very related to the results, including batch size. Maybe 64 is better, but other values also got good results. After we learned this information, we could summarize our own hyperparameter optimization experience to design better search space. Also something inside hyperparameter optimization. In addition, I could analyze detail between some trials. In this example, we open details of 3 trials. We need to analyze these 3 trials in details. First trial is in blue. There's only 1 point, and the data says it only ran 10 seconds and stopped. And the matrix output is that the final result is 0.1, or 10% of the progress, or almost no effects. That is to say, it is early stopped. We can see that its learning rate is 0.1, maybe due to this reason, because it's early stopped. And the second red trail, the second one, the learning rate is also 0.1, or the 0.1 means that the size 1 in 10. So we could think that if the learning rate is high, it could not be learned basically. And the last result, we could see that its values are from 0.1 to around 90%. It's essentially a good result. Its learning rate is 0.01, so 0.01 is better. But how better it is, we still need to compare with other data. But under this analysis, we could see that how could a trial get good results. So if we need to have some more analyzing in trials, this interface could help you a lot. So that's all I want to say about NNI, and there are lots of other Microsoft AI open source projects available on GitHub. Feel free to choose someone you're interested in and get some more details from the GitHub site. LightGBM is a popular project on GitHub with more than 10,000 stars. The full name is Light Gradient Boosting Machine. It's a high-performance gradient boosting library. SPTag stands for Search Partition Tree and Graph. It's for approximate nearest neighbor search. OpenPy, or Open Platform for AI, is an AI computing resources managing system. Neuron Block is for building NLP-DNN models. NMDNN is a set of tools to help users interoperate among different deep learning frameworks. Deep image analogy is a technique to find semantically meaningful dense correspondences between two input images, just like these horses. Deep Feature Flow provides a simple, fast, accurate, and end-to-end framework for video recognition. Okay, hello again. That's all of the talk of today, and finally, at the end of the talk, I want to say welcome to use, give feedback, or even do some contribution to NNI and also other interesting AI open source projects from Microsoft. Thank you.